Very good afternoon, dear students. So today we are going to start a new topic, that is filters. And we all know, or we are aware of the term filter. In fact, in our day-to-day routine life also, we use filters at so many places, but those are physical filters. And here in today's class, we will talk about electrical filters. Okay, but the purpose of the filter is same. So what does filter do? It filters out unwanted material, and it allows the desirable material to pass through. Similarly, if we define electrical filters are those electrical networks which allow certain signals to pass through and which allows the rejection of the undesired signals. Okay, so that is the meaning of your filters. So let us start. So as I just told you, filter is an electrical network that can transmit signals within a specified frequency range. Okay, so let me tell you, it is the frequency of the signal that will decide whether it will be able to pass itself through a given electrical network or not. Okay, so if the frequency range of the input signal lies within the pass band of the filter, it will be passed, and if it lies outside the pass band of the filter, then it will be rejected. Okay, so in any filter we'll have two bands. One is known as pass band, and another is known as stop band or attenuation band. So students, if I talk about ideal filter, uh, you, you can say perfect filter. Perfect filter will pass the signal as it is, which lies in the pass band. Okay, and the perfect filter will reject the signal totally, which lies in its attenuation band or the stop band. So if we try to visualize uh, the concept of ideal filter, its frequency response looks like this. Okay, so in case of ideal filter, we have sharp cutoff profile. What does it mean? That within the pass band, your signal will be passed as it is. This is the pass band. Okay, your signal is passed as it is, and as soon as your pass band is over, then your signal is completely attenuated. There is no single instance of the signal or the frequency outside the pass band that can come out of the uh, filter. Okay, and the frequency which demarcates the pass band and the stop band, that frequency is known as cutoff frequency. Okay, so cutoff frequency is an important parameter in case of our filter, which distinguishes between your pass band and the stop band. Okay, so you can see in the two figures on the left hand side, I have shown the pass band. So this is the pass band. Okay, and outside pass band we have stop band for the case of ideal filter. So similarly, in the second figure, we have, this is the pass band, fine, and this is your stop band. Okay, in the above figure, we have the passband frequencies on the lower side. That's why we call it as low pass filter. Uh, in, in the figure at the bottom, the frequencies which are being passed, they lie on the higher side of the graph. That's why we call it as high pass filter. Okay, so the filter which passes high range of frequencies, that is known as high pass, and the filter which passes lower range of frequency spectrum, that is known as low pass filter. And the frequency which distinguishes the two bands, that is known as cutoff frequency. Okay, now let us talk few more things related to ideal filter. As I told you that your ideal filters, they have sharp cutoff profile. Okay, sharp cutoff profile, it means that your filter response frequency response of the filter will look like this. This is known as sharp. It is also known as brick wall filter. Brick wall. Okay, means it resembles like a brick, and you all know that the edges of a brick that we use in wall, it has sharp edges. Okay, so sudden change takes place, it's not gradual. Okay, this is known as sharp cutoff profile. Okay, but these ideal filters are only theoretically possible. If we try to realize ideal filter, these filters are not realizable. Means you cannot design ideal filter with the help of your components, whether active component or passive component. You cannot design ideal filter. So ideal filter is just a theoretical concept. You try to remember this thing. Okay, so what is the solution then? Practically, the kind of filter that we are able to design, that filter is called as practical filter. Now what will happen in practical filter? In practical filter, we will not have sharp cutoff profile. Means your cutoff profile will not be sharp like this, it will be gradual like this. Okay, so it will not at once come to zero, it will come down like this gradually. Okay, now you see in the figure clearly the orange line, it shows the gradual change in the, you can say, pass band of the filter. Okay, so now you see here that in the pass band of this low pass filter, certain frequencies are also being passed by the filter. Okay, this range of frequencies are also passed, though the amplitude of these frequencies passed is, you know, cut by the filter, or you can say attenuated. Those frequencies are attenuated, but they do appear at the output. Okay, similarly, in case of high pass filter, your ideal uh, band would have passed only these frequencies, whereas in case of practical filter, you are basically bound to allow certain frequencies which are adjacent to the pass band, though these frequencies are having attenuated profile, but they are being passed. Okay, so in case of practical filters, we are not able to completely suppress the signal in the stop band. So I hope this thing you have understood. So and you also know in our day-to-day life, in our practical life, we cannot have anything perfect. Obviously there are certain defects, whatever small those defects may be, but we cannot have 100% perfect thing. So same thing applies to filter as well. We cannot have 100% perfect filter. We have practical filters which are imperfect. Okay, so I hope this concept is clear to all of you. Now let us move forward. So students, we have two types of filters. One is active filter and another is passive filters. So the today's class will be dedicated to passive filters. In fact, in the topic which is there firstly in this unit is passive filter, and then we will move to active filter. Just for the clarity of concept, I am explaining you what are active filters and what are passive filters. So active filters are those filters which contains active components. Okay, active components means they will have certain components which amplify the signal or which introduces gain into the signal. Okay, so and one such component is operational amplifier. All of you must have studied operational amplifier in your analog electronics. So active filters are those filters which contain active components like operational amplifier, which are able to introduce certain gains into the signal. Okay, so what is the meaning of gain? See, let me tell you, when I draw the frequency response of the signal. Okay, so here we have, say, amplitude, and on x-axis we have frequency. Okay, and this straight line is at value 1. So what does it mean? That whatever in case of filter, whatever input signal comes, whatever input signal comes inside a filter, say this is a filter, this block is say filter. Okay, so whatever input comes, filter is expected to pass that signal as it is. So there should not be attenuation if it is any in the pass band, and there should not be any amplification. That is a normal definition of filter. Whereas your active filter will introduce some gain into the signal. Okay, so that is the difference in case of your active filter. Another thing is we have some RC feedback circuits. We have some feedback circuits. RC means your resistance and capacitance. And what is the purpose of these feedback circuits? With the help of these feedback circuits, we are able to get the desired frequency response. Means the frequency response of the filter can be manipulated, or can be, you can say, optimized, more precisely, I should say. Okay, so means we are in a position to uh, idealize the frequency response with the help of feedback circuits. Fine. And to give you just an idea or overview of the circuit of the active filter, I have shown active filter on the left hand side of this slide. You can see this is your operational amplifier, and you have resistance and capacitance which are providing feedback from output to the input. So rest details we will look into when we discuss active filter in detail. This is just for your concept building. Now the main emphasis in today's lecture will be on passive filter. And passive filters are those filters which will contain passive components. And we all know passive components are your resistance, inductance, and capacitance. Okay, so here these passive filters will contain impedances in the form of L and C, which can be arranged either in series or in parallel, and both series and parallel combination will be there. Okay, and two types of network we will study in these filters. One is known as T section, and another is known as pi section. So you know what is the meaning of T? T is written like this, and your pi is written like this. So if your branches are arranged in the form of T, it becomes T section filter. And if the branches of the filter are arranged in the form of pi, it becomes your pi section filter. So if you look at the second figure in this slide, it is nothing but the pi section. I hope you are able to identify. So we will also see the T section in the coming slides, so that confusion will be over once you see that. So this is the difference between your active and passive filters. Next. So next, the properties of a filter. So though we have already talked about these properties in these previous slide, but just for the sake of completeness, I'll again tell you, and few things are new also here. So first and foremost property of your filter is characteristic impedance. Okay, so your characteristic impedance, every filter is an electrical network. Fine. So so we already have talked about two port networks. Okay, we have also seen certain electrical networks. So every electrical network has its impedance. Okay, so since filter is also an electrical network, so filter also has its impedance. And we have talked about driving point impedance in your network synthesis. So that driving point impedance for your filter is called as characteristic impedance, and we represent that characteristic impedance by Z naught. Okay, and why are we giving so much emphasis on characteristic impedance of a filter? That is so because your filter is an auxiliary circuit in the main circuits that we will be having in your electronics. Okay, so what does it mean? That you have some electronic system. Okay, says this is some subsystem, electronic subsystem. Okay, and you need to connect say some filter at the input of this system. Okay, say this is a filter, and you provide input signals, means you want to provide a filtered input to some electronic subsystem. Okay, so what is the job of the filter? That to provide the maximum part of input to this system. Okay, so in fact in the coming semesters also you will understand this concept. Okay, and that means that your characteristic impedance of the filter must match with the impedance of this electronic subsystem. Okay, so if the impedances of these two blocks they are matched, then your maximum signal will be transferred. All of you must have studied maximum power transfer theorem. Okay, so that is also in that direction. We all know that your maximum power transfer takes place when your input impedance matches with the load impedance. So same is the case here. So if the characteristic impedance of the filter matches with the circuit to which it is connected, we'll be able to transmit maximum power. Okay, and that will prevent your reflection losses. If there are reflection, then obviously the signal loss takes place. So that is characteristic impedance. Then we have just seen the passband characteristics on the left hand side of this slide. These are nothing but your passband characteristics or stop band characteristics. So in case of passband, minimum attenuation takes place, and in case of stop band, your high or maximum attenuation takes place. So you can see here the amplitude is decreasing, that's why attenuation is taking place, and here amplitude is more or less constant, that's why minimum attenuation is taking place. Okay, then we have also talked about cutoff frequency, which distinguishes between your pass band and stop band. And we have already talked about that in case of ideal filter, the transition frequency region, it will be abrupt, means sudden change will take place. Whereas in case of practical filter, this transition frequency range is, this region is larger. But we should ensure that this transition region, it must be very small as possible. Okay, so these are the properties of a filter. Next, so now we need to classify different types of filters, and we are going to study all these filters in our syllabus. Fine, so how do we classify filter? One way is to uh, classify filter is depending on the relationship between series arm impedance and shunt arm impedance. Okay, so we will just have a look at the structure of the filter in the coming slides. What is the meaning of series arm? Like we have seen such network. Okay, this is a T filter. Fine, so these are known as series arms, and this is known as shunt arm. Okay, so depending on the relationship between these series arms and shunt arms, we classify filter. And one such classification is constant K filter. These are also known as prototype filter. And why are we calling it as constant K filter? When we multiply the impedances of series arm and shunt arm, like impedances of these arms, it gives us a constant. Okay, that's why these are called as constant K filter. So any filter which gives us Z1 into Z2 equal to K equal to R naught square, where R naught is some design impedance. Okay, if R naught square is a constant, we call that filter as a prototype filter or constant filter, constant K filter. Fine, this is one category of filter. Another category of filter is M derived filter. So this M derived filter we'll discuss later on. Right now, you can assume that this M derived filters are also uh, somewhat correlated with your constant K filter. The only thing is the impedances of your series arm and shunt arm, they will be uh, derived by using certain factor, and that is known as m. So these series arms and shunt arms will be multiplied by a factor m, and we call them as m derived filter. That is one thing. Second thing is m derived filters will give us better frequency response as compared to constant k filter type. Okay, so that is another advantage. So other things will be clear when we talk about m derived filter in detail later on. Next category of filter is on the basis of their frequency band characteristics, and this is pretty known to all of you. We have low pass filter, high pass filter, band pass filter, and band stop filter. So low pass filter, they passes frequencies from 0 to fc, and they stop frequencies from fc to infinity. If we assume that our frequencies are extended from 0 to infinity, okay, and somewhere we have fc in between. So with this we define these. So for high pass filter, what we have, it will pass frequencies from fc to infinity, okay, and it will reject frequencies from 0 to fc. Fine. Then in case of band pass frequency, band pass filters, we have two cutoff frequencies. So it will have a frequency response like this, like this. So we have one cutoff frequency, that is f1, another cutoff frequency f2. So band pass filter passes frequencies between f1 and f2, and greater than f2, and from 0 to f1, these frequencies are rejected by your band pass filter. So from 0 to f2, that comes under attenuation band. From f1 to infinity, that comes under your attenuation band. So here it has taken f2 is the lower frequency and f1 is the higher frequency. Now the reverse thing takes place in band stop. In band stop, your frequency response will look like this. It will pass frequencies like this. From 0 to f1, the frequencies will be passed. From f2 to infinity, the frequencies will be passed. Whereas the frequencies between f1 and f2, these frequencies will be rejected. Okay, so these are your band stop filter. I hope everything is clear up to this point. So students, now we see the concept of constant K filter, that is your prototype filter. And I just told you in the previous slide that how do we define constant K filter. So for constant K filter, the multiplication of Z1 and Z2, that is your series impedance, series arm impedance and shunt arm impedance, they give us a constant value, that is K. And this K is equal to R naught square, where R naught is a real number and it is independent of frequency. Okay, that's why it is a constant, and we call R naught as design impedance. This R naught will be used while we design constant K filter, as we will see in the examples at the end. Okay, so this R naught is a design impedance. So as I told you in the classification of filters, that every filter will be of the type either low pass filter, high pass filter, band pass filter, or band stop filter. So your constant K filters or prototype filters, each of these filters can be low pass, high pass, band pass, or band stop. So we will look at the circuit or the structure of these different types of filters under the category constant K filter or prototype filter. Okay. So first is constant K low pass filter. So you see in constant K low pass filter, we have two types of configuration. One is known as T configuration and another is known as pi configuration. So you see here in T configuration, we have in the series arm inductors and shunt arm is having capacitance. So in pi configuration, we have L in the series arm and C by 2 in the shunt arms. So on the right hand side, we have the frequency response. So your lower frequencies lie in the pass band up to cutoff frequency, and the frequencies higher than cutoff frequencies, they are stopped. Okay. So students, before we move forward, I want to explain here that how does the circuit shown here behaves like a low pass filter. So if you understood this concept here, then it will be easier for you to correlate these circuits, and you may not be required to cram these circuits. Okay. So let me tell you, we know we represented inductor with the help of Laplace transform like LS. Okay. And your capacitor was represented through Laplace transform as 1 by Cs. Okay. And your S, this was Laplace representation. We also have some sinusoidal signal representation where we substitute S as j omega. This S is nothing but a complex frequency. When you read in the text now, you will be able to know that this S is a complex frequency. So if you substitute this thing here S equal to j omega, then your inductor is represented like this. The impedance of the inductor is j omega L. Okay. Similarly, your capacitor can be represented as 1 by j omega C. Okay. So omega is nothing but 2 pi f. So what we have done, we have represented our inductor and capacitor in the form where some frequency is shown. Okay. So in the transient response also we have talked about this thing. So now you see here that here, if your frequency is 0, then your reactance of the inductor is 0, say XL. This XL is the reactance. So XL is equal to j omega L. So this XL is 0 for omega 0. Okay. And this XL is infinity for omega equal to infinity. And this is the reactance. So what does it mean? That when we have 0 XL, that means it is a short component. And if we have infinite reactance, that means it behaves like an open circuit. Okay. Like if this is an inductor and XL is 0, then your inductor become a short. Okay. Simply like a wire. And if your reactance is infinity, then your inductor will behave like an open circuit, means nothing can go from here to here. There is an open circuit. Similarly, for the capacitor, reverse things takes place because omega is in the denominator. So for omega equal to 0, your capacitive reactance is infinite. And for omega equal to infinity, your capacitive reactance is 0. Okay. And what does it mean? That for zero frequency, your capacitor behaves like a short circuit. I'll write with SH. Okay. Sorry. For zero frequency, your capacitor will behave like an open circuit, not short, sorry. And for infinite frequency, your capacitor will behave like a short circuit. Okay. And what is the meaning of zero frequency? Zero frequency means DC. Omega equal to 0 means DC. We know that DC is nothing but zero frequency. Okay. Or you can say low frequency. And omega equal to infinity means high frequency. Okay. So now let us see here what happens when omega is 0, means low frequency. For zero frequency, your inductor will be short. So this is a short. This will also be short. Okay. For zero frequency, your capacitor is open. means it will be open. It means it will be removed. Okay, in a way, for zero frequency, this circuit becomes like this, like this. It is short, so connected with a wire, it is open. What does it mean? Whatever you give at the input, exactly same comes at the output. In which case, for zero frequency means low frequencies. It means it is passing you the lower frequencies as it is. Okay, now let us see the higher frequencies. So for higher frequencies, what happens for omega equal to infinity? For higher frequencies, this inductor, it becomes open circuit. Okay, for higher frequencies, this inductor also becomes open circuit. For higher frequencies, this capacitor become a short. Okay, so how does this circuit look like? This circuit looks like this. You have an open circuit. Okay, and here you have short. These two inductors, they are open circuit. Means whatever you provide at the input, it cannot go at the output because this circuit is not connected at all here. Okay, means higher frequencies, they are not allowed to pass through. That's how your this circuit behaves like a low pass filter. I hope this thing is clear to each and every student. Now same logic you apply to this pi configuration and you will be able to at once justify the use of this circuit as a low pass filter. So students, this way your low pass filter works, and now we will see its further analysis and design. So in this slide, we have a constant K high pass filter. You see, in case of high pass, your inductors and capacitors are interchanged. If I go back, see here we had inductor in the series arm and capacitor in the shunt arm. Okay. And whereas in case of high pass, we have capacitors in the series arm and inductor in the shunt arm. So this is T configuration. Similarly, we have pi configuration, C and here. One thing also you need to notice, you see here that in the series arm, we have represented C with 2C. Okay, in this T configuration. Why are we doing that? We know that in case of your series, your impedances or reactances, they are added together. Okay, so and in case of your parallel combination, we know that your parallel combination of resistances or reactance formula takes place. Fine. So if you see here that this is 2L 2L, the purpose of having such thing is that like we want to have total series reactance or impedance as say if we have capacitor, we want total impedance as 1 by Cs. Okay, fine. And in case of inductor, we want this total as Ls. Okay, so if you see here, this is 2L 2L in the parallel. So if you obtain the total, it will come out to be L. Okay, similarly in case of capacitor, the reverse takes place, so that's why it is 2C. If we go back, you see here we have L by 2 and L by 2 in series. So if you sum them in series, L by 2 plus L by 2, it becomes L. And here we had only one capacitor, that's why it is C. And here this is only single L, that is L. And in parallel, when capacitors are in parallel, so these are being added. So C by 2 and C by 2 gives us C. Okay. So same logic applies here. For capacitor in series, things becomes reverse. So that's why it is 2C, 2C, and in parallel, your for inductors, the reverse thing takes place. Fine. So now you see for the constant K band pass filter, in case of band pass, in low pass and high pass, we had either inductor or capacitor in series or parallel arm or shunt arm. Whereas in band pass, we have both inductor and capacitor. But in series arm, we have inductor and capacitor in series. And in the shunt arm, we have inductor and capacitor in parallel. Okay. This is your T section and this is your pi section. Okay, so if you see them again and again, the entire picture will be clear in your mind. So in band stop, things will change. What we presume, it should be like this, that in series arm L and C, they should be in parallel, and in shunt arm L and C should be in series. This should be the structure of band stop. Let us see if it is like that only. Yeah. So here you see, in case of band stop filter, we have in the series arm L and C in parallel, and in the shunt arm L and C are in series. Okay. So, and this is your pi configuration, and that was your T configuration. So that way, things are very easy to memorize and understand. And the concept I have already told you, that how does your inductor and capacitor behave for low frequencies and high frequencies, and you can apply that concept to in all the filters and try to understand whether it is able to pass low frequency or high frequency, or pass certain band of frequencies or reject certain band of frequency. So now we analyze the prototype filter section. Okay, we will derive certain expressions and we will use those expressions in the designing of constant K filters, whether it is low pass, high pass, band pass, or band stop. So first what we do, we try to obtain an expression for characteristic impedance, that is your Z naught. So what we have considered here, we have considered T section, and in that T section we have connected a load of value Z naught. You see, Z naught is the load impedance. Okay, and our input impedance is Z in, and this Z in also we will take as Z naught. So again, think of that maximum power transfer theorem. What we are doing, we are trying to make our input impedance equal to load impedance, and our input driving impedance is nothing but characteristic impedance. So we are trying to match the two. Okay, so if we do that, then we will find out the value of characteristic impedance Z naught for T section. Okay, and that expression will come out to be this one. So Z naught is characteristic impedance, T means for T section. If we had pi section here, then we would have written Z naught pi. Okay, let us see how this expression has come. It is very, very simple. So we have already seen the structure. Let me go back. See, we had L by 2, L by 2 and C here in the T section. So that's why here we have shown Z1 by 2, Z1 by 2, and this is Z2. So our series arms are represented by Z1 by 2, Z1 by 2, and our shunt arm is represented as Z2. Okay, in fact, this is our generalized expression. So if your series arm contains inductor, okay, we know that, say, sorry, for inductor, your what is Z1? Z1 is nothing but J omega L. Okay, so what we have, Z1 by 2. So Z1 by 2 will be J omega L by 2. So what is inductor value? Inductor value is L by 2. That's why L by 2 was shown there. See, L by 2. Fine. and this was Z2. Z2 is nothing but your 1 by j omega c. So c remains as it is. Okay, so now we have to obtain the value of characteristic impedance. So see, we want to find out input impedance. For input impedance, these two impedances, they are in series. Okay, the series combination of this is in parallel with Z2. See here, Z1 by 2 and Z0, they are in series. That's why they are added. This is in parallel with Z2. So this is your parallel combination with Z2. And this entire thing is in series with Z1 by 2. So you see, this entire thing is added with Z1 by 2. Okay, and this input impedance we have made equal to Z0. Okay, so this expression you have to solve. We know the parallel combination formula that has been applied here. Okay, so if you solve it completely, you will get Z0 square equal to Z1 square by 4 plus Z1 Z2. And what will be Z0? Z0 is equal to under the root Z1 square by 4 plus Z1 into Z2, where Z1 is series arm impedance and Z2 is your shunt arm impedance. And this formula is very, very important, and as it will be utilized in your every design numerical of your constant K filter. I hope this derivation is clear and it is very, very simple. Now let us move forward. Next step after design impedance is the determination of propagation and attenuation constant. Okay, so your propagation constant is represented by gamma. Okay, and gamma is equal to alpha plus j beta, where this alpha is known as attenuation constant and beta is known as phase shift constant. Okay, I hope this thing is clear to all of you. See, your gamma is alpha plus j beta. Gamma is propagation constant, alpha is attenuation constant, and beta is your phase shift constant. So for designing of the filter, we will also require this alpha, beta, and gamma. Attenuation constant will tell things us about the attenuation or pass band or stop band. Okay, so for pass band, the value of alpha, because it is attenuation constant, obviously it should be 0 for your pass band. Okay, and it will have certain constant value for the stop band. Fine, I hope this thing is clear. So now let us find out the expression for your propagation constant. Okay, so we define propagation constant as e raised to power gamma equal to is by ir. Okay, and how do we define this is and ir? See, you look carefully this formula. So here, this is again T section that we saw in the previous slide, this one. Okay, so here you see is the current in this Z1 by 2 branch. Okay, that is in the input side, and IR is the current in the output side. And in the shunt arm, what will be the current? Is minus IR. Okay, and we define e raised power gamma as is by IR. So now I leave it to you to find out the ratio of is upon ir, because by simple application of KVL, that is Kirchhoff's voltage law, we can determine these values. And if you solve for is and ir, you will get this ratio. Okay, so your e raised to power gamma becomes this one. Okay, and you see here, you have Z naught here and you have Z naught here. So you apply KVL concept and find out the value of is by ir, and you will get this. Now Z naught, we already know it is characteristic impedance. Okay, so if you substitute this value of Z naught here, you get this. We have just seen in the previous slide the value of Z naught. It was under the root Z1 square by 4 plus Z1 Z2. Fine. So if you substitute, you get e raised power gamma here. Now we need to calculate e raised power minus gamma. E raised power minus gamma is nothing but 1 by e raised power gamma. So that's why it is written as 1 by this. Now what we do, you rationalize this. You already know what is the meaning of rationalize. You multiply numerator and denominator by 1 plus 2z2 minus this. Okay, so with this minus you multiply in the numerator as well as in denominator, you will get this. So this is, you have got e raised to power gamma, and this is how you have got e raised to power minus gamma. Then we sum them together, e raised to power plus gamma and e raised to power minus gamma, we get this. We divide by 2, we get this. Now I hope you are able to recognize this, because all of you have studied mathematics. Okay, so e raised to power gamma plus e raised to power minus gamma by 2 is nothing but cos hyperbolic gamma. So cos hyperbolic, sine hyperbolic, you already know. So cos hyperbolic is e raised to power gamma plus e raised to power minus gamma by 2. So cos hyperbolic gamma is 1 plus z1 by z2. This is second important formula that you have to memorize. One is last one, that is z naught is equal to under the root z1 square by 4 z2 square plus z1 by z2, and second is this one. Okay, now one important concept that we need to understand, that once we have determined characteristic impedance, that is z naught, if the value of z naught is real, okay, then attenuation will be 0. Okay, so zero attenuation means pass band. Okay, so it means for the pass band the value of characteristic impedance will be real and attenuation will be 0. If our characteristic impedance is imaginary, okay, it means that our attenuation alpha will be some constant value and not equal to 0. And what does it mean? That it is stop band. So in other words, we can say that in pass band our z naught will be real, and in stop band our z naught will be imaginary. This you have to memorize, because it will be required in the designing of the filter. I hope it is clear to each and everyone. Now let us move forward. So now we, in the previous slide, we generalized the expression of your z naught and cos hyperbolic gamma. Now we specifically come to analysis of prototype low pass filter. We take specifically low pass filter. Okay, as we had seen, this is your T section of low pass filter, and this is our pi section of our low pass filter. Okay, so here you see, in case of T section and pi section, how much is the total series impedance? This plus this, and this will come out to be j omega L by 2 plus j omega L by 2. It gives us j omega L. This is Z1 is how much? J omega L. And how much is the shunt impedance? That is Z2 is equal to 1 by j omega C. And since j is your complex number, if you multiply in the numerator denominator, you get minus j by omega C. So we have seen Z1, we have seen Z2. Now what was the condition for our constant K low pass filter or constant K filter? The condition was that Z1 into Z2, it must be equal to some constant K. So we need to now find out here that what is the value of Z1, Z2. If we do that, Z1 is j omega L, Z2 is minus j omega C, we get L by C, where L is also some constant, C is also some constant. It means this Z1 into Z2 is some constant K, and that we equate to the design impedance, that is your R square. Okay, so for case of prototype low pass filter, Z1 into Z2 is equal to L by C equal to R naught square. This equation you have to memorize for your prototype low pass filter. Okay, second thing. Second thing is the expression for characteristic impedance we have already seen. Z naught T was under the root Z1 Z2 multiplied with 1 plus Z1 by 4 Z2. I hope you are able to recall. Just let me go back and I'll show you the value of characteristic impedance. See, this was the value of characteristic impedance. So this value we have again modified in a way that, like, what we are doing under the root, we are taking common Z1, Z2, and inside what we are left with, 1 plus Z1 by 4Z2. Okay, this is what we get from this. So same thing we have written there. See, Z1, Z2 into 1 plus Z1. So this is nothing but your characteristic impedance of T section, as we saw in the previous slide. Okay, so we have obtained Z1, Z2. So for obtaining Z naught T, we have Z1, Z2. Now we also need to obtain Z1 by 4 Z2. So what is Z1 by 4 Z2? It is this. You simply substitute the value of Z1 and Z2, you will get this. Okay, so your Z naught T becomes under the root LC, and like this. Simply substitute all these values and you will get this. If you further solve, see what is under root LC? Under root LC is nothing but R naught. So this under root LC R naught has been substituted. Okay, then we have substituted 4 by LC as omega C square. So then your expression becomes like this. Z naught T equal to R naught under the root 1 minus omega square upon omega C square. And omega you already know 2 pi F, and omega C is 2 pi FC. If you do that, you get this expression. Your Z naught T becomes R naught is equal to under the root 1 minus F upon FC square. So you see here, just by looking at this characteristic impedance expression, we are able to say that this filter is a low pass filter. How? See, I told you that for pass band, your characteristic impedance, it should be real. For this to be real, the value of F, it must be less than FC. If F is less than FC, this term will be less than 1, and this entire term will be positive, and your under the root will be positive. That will give you constant positive value. Okay, so when F is less than FC, your Z naught T is real. It means it passes those frequency, means it is pass band. So it means it passes low frequency. Now for high frequency, that is F greater than FC, this will be greater than 1. If it is greater than 1, then the entire thing under the numerator, it will be negative. And we know that if we have negative value under the root, then it gives us imaginary. Imaginary means Z naught is imaginary and it gives us stop band. So just by looking at the characteristic impedance expression, we can make out whether it is the characteristic impedance of low pass or high pass or band pass or band stop. You can see one example we have seen here just now. Okay, so this was the characteristic impedance analysis of your prototype low pass filter. Now, this is, I just explained to you. You see here, Z naught T is real if this term is less than 1. Okay, and if it is greater than 1, it will be imaginary. Okay, so this is omega square LC by 4 term. Okay, now what will happen when omega square LC by 4 equal to 1? Okay, see in the previous slide, we had substituted omega C square as 4 by LC. Otherwise, our original expression was this one only. Okay, so just a minute. See, this was our original expression. So here, if omega square LC by 4 is less than 1, it is real, that is pass band. If omega square LC is greater than 1, it means it is imaginary, means stop band. And what happens when it is equal to 1? If it is equal to 1, it means it is distinguishing between pass band and stop band. And what is that parameter which distinguishes your pass band and stop band? That is nothing but your cutoff frequency. That means if omega square LC by 4 equal to 1, that will give us cutoff frequency. And the cutoff frequency for your prototype low pass filter will be 1 by pi under the root LC. That's it. So what we have done for prototype low pass filter, we have obtained the characteristic impedance value. We have obtained the characteristic impedance value in the form of F and FC. Okay. We have obtained the value of Z1 into Z2, that is equal to L by C. And lastly, we have obtained the value of cutoff frequency for prototype low pass filter. Okay. So this was for T section low pass filter. Okay. Similarly, for pi section also, we have to determine all these things. And luckily, your pi section things can be directly derived from your T section thing. Okay. So for this, if you have gone through thoroughly your two-port analysis, there also we had T section and pi section thing in the book. Okay. So you can also again go through that. So for pi section characteristic impedance, that is Z naught pi, the formula is Z1 Z2 by Z naught T. So if you apply this formula, you will directly get the characteristic impedance of your pi network. So uh, this was our characteristic impedance for T section. For pi section, Z1 Z2 divided by this. That's it. So if you do that, we know that Z1 Z2 is what? Z1 Z2 is nothing but R naught square. This we have taken from previous slide. Okay. And if you solve this, this becomes your characteristic impedance for your Z naught pi. Fine. So here also same logic apply. If F is less than FC, this will be real, means passband. If F is greater than FC, it means it is imaginary. It means your stop band. So this is your characteristic impedance for your prototype low pass filter T section as well as your pi section. Let us now move forward. Now we will find out propagation constant, that is your gamma. Okay, this expression I have already told you that cos hyperbolic gamma is equal to 1 plus Z1 by 2 Z2, where gamma is alpha plus J beta. Now in this prototype low pass filter, what we have to do, we have to simply substitute the value of Z1 and Z2 for our T section or pi section. So that's what we have done. So 1 plus Z1 by Z2, we have substituted the value of Z1 and Z2, we get this. Okay, we had obtained Z1 by 4 Z2 as this one. Now this is Z1 by 2 Z2. So this becomes omega square LC by 2. So what we get for your prototype low pass filter as cos hyperbolic gamma equal to 1 minus omega square LC by 2. And your gamma is alpha plus J beta. So if you apply trigonometric formula, you get cos hyperbolic alpha plus cos beta plus j sine hyperbolic alpha plus sine beta equal to this one. Okay. Now this expression can be further derived depending on our conditions. We already know that for pass band, our alpha is what? 0. Fine. And another thing that you see here, that the right hand side is a real value, and on left hand side we have a complex number. This is real part and this is imaginary part. So you can see that since there is no imaginary part on the right hand side, so sine hyperbola alpha into sine beta, this is nothing but equal to 0. Okay, and cos hyperbolic alpha cos beta is equal to 1 minus omega square LC. So this expression, if you remember, you can use it in the design numericals of your any constant K filter. Fine. Now, so these are the design equations, and these design equations have been obtained from whatever analysis we have just seen in the previous slide. For prototype low pass filter, we obtained Z1, Z2 as L by C equal to R naught square. So from this, what we get, design impedance R naught is equal to under the root L by C. This is one important equation. Another thing we had seen regarding your cutoff frequency, for cutoff frequency, omega square LC by 4 was 1. So if you solve it, what do we get? The cutoff frequency as FC is equal to 1 by under the root, sorry, 1 by pi under the root LC. Okay, so if you use these two, R naught is equal to under the root L by C and FC, you will get this. L is equal to R naught by pi FC and C is equal to 1 by pi R naught FC. You can multiply these two and you will get this. Okay, so this is known as design of prototype low pass filter. What we are doing, we are given design impedance, we are given cutoff frequency. From these, we identify the value of L, we identify the value of C. So design of a prototype low pass filter means the selection of filter components by using design impedance and cutoff frequency. So normally we are given that we want a prototype low pass filter with certain cutoff frequency. We want a prototype low pass filter with certain design impedance R naught. Then what value of inductor and what value of capacitor should we take so that we are able to get the desired thing. So this is your design of prototype low pass filter. Okay, so with this, the concept of constant K prototype low pass filter is over. I'll discuss two numericals related to that, and that will complete our prototype low pass filter design. Now let us move further. So see, in this numerical example, we have been given a T section low pass filter, okay, which has series inductance as 80 millihenry. Okay, this is total series inductance, means we are given Z1, okay, or you can say L. Okay, so 80 millihenry, we are given shunt capacitor value as 0.022 microfarad. Now here we have to determine the cutoff frequency and design impedance. Okay, and after doing that, we have to design an equivalent pi section also. So very simple. We have L, we have C. We need to first determine cutoff frequency. The formula for cutoff frequency is this one: Fc is equal to 1 by pi under root LC. We substitute the value of L, 80 millihenry, then capacitance in microfarad, and if you solve, the cutoff frequency is 7.58 kilohertz. Then we need to find out design impedance. For design impedance, the formula is under the root L by C. We substitute value of L and C, and the design impedance comes out to be 1.907 kilo ohm. So if we represent that in the form of T section, this is what we have done. In T section, what we have, we are given L. We are given L, 80 millihenry. But in the T section, we have L by 2. So in T section, instead of 80 millihenry, it will be 40 and capacitor as it is. Fine. So this is important thing that I wanted to point out, that you need to memorize, or you need to be careful that this is L by 2, whereas in case of pi section, you have C by 2 and C by 2. Fine. So now for pi section equivalent, you have L here. So L completely comes 80 millihenry. Then here you have C by 2, C by 2. So that's why your capacitance values are halved. So if I this is your equivalent pi type low pass filter. I hope this thing is clear to everybody, please. So next we have a second numerical example. Fine. So here we have to do the reverse thing. Now we have to design low pass filter, and we are given R naught and cutoff frequency. So we have to design a constant K low pass filter. Cutoff frequency is given, design impedance is given. So we will apply the formula for L, which is R naught by pi FC. We substitute all the values and we get the value of L as this one. Okay, then we need to find out shunt capacitance, for which the formula that we derived is C equal to 1 by pi FC R naught. If we substitute, we get this value of our shunt capacitance. Okay, so now we have to design, because it is written low pass filter, it is not mentioned whether we have to design T section or pi section. So obviously we'll have to design both. So for T section, it will be L by 2, which will be half of this. We have done that. Capacitor will be as it is. That's it. We have designed T section K constant K low pass filter. For pi section, it will be L here, and then C by 2, C by 2. So half of this. So this we have shown. Now we were given one more thing, and we need to find out the value of attenuation. And what is attenuation? I told you alpha. Fine. And though I did not derive this expression exclusively, but the expression that I had shown you for propagation constant and attenuation constant, from there you can determine this expression very easily. So your alpha will be twice of cos hyperbolic inverse f alpha by fc. Okay, so fc is your cutoff frequency, and we need to find out the value of attenuation at 4 kilohertz. We know attenuation will change with the change in frequency. Okay, so this value of f alpha is 4 kilohertz, fc is 2 kilohertz, and you substitute the value of alpha, that is attenuation constant, comes out to be 2.634 nepers. This you remember, the value of this attenuation constant will be having unit as nepers. Okay, so this is how we complete our design of constant K low pass filter. And in the similar fashion, we can design high pass filter, band pass filter, band stop filter. Their design equations will be a bit different, and in the coming classes we will talk about the remaining type of constant K filters, that is high pass filter, band pass filter, and band stop filter. And once we are complete with constant K filters, then we will move to your M derived filters. So for today, this was the final thing that I wanted to discuss. So I stop here.